Advanced Financial Modeling, Topic 9, Forecasting Financial Statements, Free Cash Flows, Stock Valuation, and a bonus topic, we're going to simulate correlated random variables. So before we do that, I want to generate a model to forecast the cost of gas for this firm, and then I'm going to show you how you can work in the idea or the concept of correlated random variables. So let's go to the model. And you can see the uncorrelated tab here. This firm requires 1 million barrels of crude oil and 10 million gallons of gas. Oil selling for 75 a barrel. Gas is selling for 350 a gallon. Oil spot price is expected to go up by 4%, gas by 3%. Oil and gas standard deviations are given. And you assume that oil and gas tend to move together. They tend to both go up and down at the same time, but they're not perfectly correlated. We'll assume 0.7. So let's go ahead and get the expected oil price going up by 4%, gas price going up by 3%, and then the expected cost. No simulation here. It's just 1 million barrels times the expected price of oil and 10 million gallons times the expected price of gas. And then I want to do is run a simulation to see the cost, which should be right around 114. But I also can use that simulation of, say, 10,000 possible prices of oil and gas to get, say, the 5% highest, 5% lowest, a probability. But all I've done here is I've just gotten the standard deviation of costs. So I also want to show you this model because this is a different way of doing a simulation we haven't done before. Normally, I run a macro. I would create a formula for the simulated price of gas, the simulated price of oil, and the unhedged cash flow. And then we take that formula, copy it 10,000 times, and then that norm S inverse RAND function generates 10,000 possible prices of oil and gas. But here's what I did. I'm not going to use a macro. I've numbered this array here, 1 through 10,000. Notice I've hidden rows 22 through 10,016. But here are the 10,000 iterations. And then here is a random standard, we call it a standard normal random variable, norm S inverse RAND. And then I did another one here. So here are 10,000 standard normal random variables. Here are 10,000 standard normal random variables. Now, again, the terminology. If I just did the RAND function, that would just be 10,000 numbers between 0 and 1 with a mean of 0.5. But using norm S inverse RAND, now these, if you were to graph these, look like a bell-shaped curve. The mean of this column of 10,000 random numbers is 0. The standard deviation is 1. So whenever you have an array, a series of numbers that is normally distributed with a mean of 0 and a standard deviation of 1, we call it standard normal. So, and you see, if you look at all these numbers, there's just a lot of numbers between -3 and 3, most of them between, say, -1 and 1. So these are two arrays of standard normal numbers. Notice there's no connection between the two, so these are two independent random series. So I'm going to simulate the price of gas 10,000 times by just copying the formula, and every time I move down, I get a new random number. And I'll simulate the price of gas. Every time I go down, I get a new random number. And then I get the total cost. It's the simulated price of oil times times the minus quantity of oil, and the simulated price of gas times the 10 million gallons. And so you can see now every time I hit F9, I get 10,000 possible prices of gas. So all I need to do is take an average of those 10,000 numbers, and I could maybe just get the standard deviation. But make sure you can also do things like, what's the probability of paying more than, say, $140 million, or what's the 5% highest and lowest. Make sure you can do the small and large also. So this is a simulation in the spreadsheet that does not require a macro. So it's just another way of doing it. The other thing I can do sometimes for the spreadsheet to work faster, I could just copy these and paste them as values. So copy all these random numbers and paste them as values, because I don't really need it to update every time I hit F9. I just need a set of 10,000 randoms. All right. Notice the correlation never came into play here. if I recalculate the correlation between these two random series, it is about 0. And I have F9 enough times that it'll be about 0. So it's usually between negative 0.01 and 0.01. Okay, so they're uncorrelated, 0 or independent. But how do I build in the fact that when oil goes up, gas goes up. When gas goes up, oil tends to go up, and the other way around. What I need to do is not have independent, uncorrelated random numbers. What I need to do is have correlated, that when I run the correlation, they have a 0.7 correlation. In other words, once this, say you think about the process, how I do this, I need to generate the first random number, and then once it's generated, it's more likely to generate one in the same direction. In other words, if this number turns out to be -1, this one will be more likely to be in the negative range. If this one turns out to be -1 point, this one will be negative. What you see is they tend to be pretty random. Both of them, independent and random. All right, so here's what I'm going to do. I replaced those two columns with these two columns. That's all I did. The rest of the spreadsheet is exactly the same. But when I look at the data, when this one's negative, this one tends to be negative. When this one's positive, this one tends to be positive, and so on. But it's not perfectly correlated. If I actually calculate the correlation, it is 0.7. Now, when I run my simulation, which is over here, take the average, still 114, but look at the standard deviation. It's actually 29 instead of 24. Now, you can probably guess why. Because if they're correlated, they tend to both go up and down at the same time. So there's less diversification between needing both fuels if they tend to move in the same direction. So by assuming these are uncorrelated, I'm underestimating the risk. I would be underestimating, say, the 90% confidence interval. I'd be underestimating the probability that it would be above or below a certain number, because this is assuming they move in independent fashion, where in the correlated model, they tend to move together. So that's the model. The question is, how do I get a set of correlated randoms? And what I'm going to do is just, I'm going to reach into my tool bag. My tool bag has Python. I'm going to go to this Python model. I'm going to double click, Control A, Control C, go to Python, paste it. Here's the program. I'm going to run it. And let's look at the program. This program generates two correlated standard normal randoms. How I got it is from ChatGPT. I went to ChatGPT and I said, write Python code for Colab to create two arrays of 10,000 correlated standard normal randoms using a Cholesky decomposition. The arrays can then be exported to Excel. That's what I actually asked ChatGPT. Now, how do I know to use the word Cholesky? I just know from a previous life that a Cholesky decomposition is a way of generating correlated randoms. If I go to the PowerPoint, I have just a small discussion, and that is to generate correlated randoms. You need to generate a set of randoms, and then you need to use the correlation matrix to modify the two arrays of randoms. That process to use the correlation matrix to manipulate the uncorrelated randoms is called a Cholesky or Cholesky decomposition. That resulting array then turns out to be correlated. All right. And then this kind of discusses why the standard deviation was larger than we thought with correlated randoms. So I went to ChatGPT, asked it to do that, and again, back to the code. It looks like it imports the package NumPy as NP, imports pandas as PD. It sets a random seed. If you were to Google Cholesky decomposition for creating correlated randoms, that's a mouthful, isn't it? You would get what this random seed's about, but it has to start randomly with some value. This program also sets the number of variables. Looks like I'm setting number of samples to 10,000. If I added a 0 to that, I'll get 100,000 random numbers. you put in the desired correlation matrix. So in the assignment for this one, you're going to actually generate a different model with a different correlation coefficient. You just need to go in here and modify this to the desired correlation. And then what the model does, it actually generates random standard normal variables. This is just generating an array of a bunch of standard normal random variables like we did in the first model that we just talked about, uncorrelated. And then it creates a covariance matrix, which it's pretty easy for this one because it's just it's just two numbers, so it's just 1. Each number is correlated with itself perfectly and 0.7 with the other. And then it does this magic of the Cholesky decomposition. It manipulates that correlation matrix and modifies the data. And then the last step is code to send an array of data to Excel. It's using df.toExcel. It's going to call it correlated data.xlsw, index equals false, not sure what that means. And then once you run that, we're going to look for the file correlated data. So I'm going to go here. There's my correlated data. I could download, and then when that comes to my download bar, I can open that up. I can then grab these two variables, Control-Shift down, Control-C. Then I can go to my model, correlate it, and I could paste them here. And that's what I did. I notice I get the same results here. Still have a 0.7 correlation between these two. Remember, when they're here, just using these randoms, it was almost a 0 correlation. So it's really, really important when creating Monte Carlo simulations in which you have more than one random variable. If you do not specify a correlation, it will give 0 correlation. It assumes independent 0 correlations. And so you could be grossly understating, or maybe in some cases overstating values. So if you have some intuition or you have some data for correlated variables, use a Cholesky decomposition, a little ChatGPT, to generate the data. If I had 3 variables, I could modify that program to add a third variable and get a 3x3 correlation matrix. And then I'd get 3 arrays of random variables. So this is really important in running simulations, is the assumption of whether the random variables are correlated or uncorrelated. All right, so that is it. That was topic 9.